Okay. Last week we got through all new material, or at least any of the new material we're going to go over. So this week it's just going to be going through examples, practice exam examples that will likely show up on the final. The final is not going to be cumulative. Tentatively think it probably have 2 hours once you started to take it. And it probably will consist of about 15 multiple choice, and then probably 2 or 3 short answer, depending on how you kind of categorize the short answer, because some of the short answers have multiple parts. So you'll have probably, if you want to break it down, about 60 to 70% of the grade will be from multiple choice, and then 30 to 40% will come from those short answers. So short answer questions will be fairly important, but also they allow me to give a little more partial credit. So kind of expect, that's roughly what you can expect from the final. I'm still kind of finalizing a few of the questions, and so once I have kind of the exact numbers and point breakdown, I'll make sure I post an announcement about what the exam is going to look like, and then some of more of the specifics. It'll be very similar to what we've done for the other 2 midterms in terms of you'll have, except for this time, you'll have a 72-hour block to take it. Once you start, you'll have 2 hours. Uploading your answers to those short answer portions. Shouldn't be anything too new. Like I said, not comprehensive. I think originally, if you look at the syllabus, I might have said it was going to be. Syllabus, I kind of say is subject to change. I think given the format, given kind of how we're ending class here, I'm going to not make it comprehensive, which I think will kind of help a lot of you out. So let's jump into. So this week, I have, I can start working through certain problems, but if there's any specific examples for those of you who are kind of signed on live that you want to go over, we can start with those. If no one kind of pipes up, then I'll just kind of take the wheel and kind of start working through that practice exam A, which can be found under Files, Final Exam Practice Materials. We're going to be working through this Form A, okay? So I'll wait for a second, see if there's any specific questions, otherwise we'll kind of get going here. Okay, another thing I want to mention before we get started here, just some housekeeping stuff. I did push the due date to the end of the day today on that 4th Connect assignment, so that if you didn't finish it up, you can kind of work on it until the end of the day today. If for some reason it automatically submitted kind of what you had, send me an email, and if you want to, the ones that you didn't get to work through, you can still finish those today. You can submit a second assignment just working on the problems that you didn't finish, and then I'll kind of go in after today and manually kind of combine the points from those 2 attempts. I also pushed the due date forward on that 4th Excel assignment to the end of the day today, so if you did submit it and want to kind of make some revisions today and resubmit, that's okay as well. You'll have to the end of the day today to do that. And that's because not your section specifically, I had kind of a family emergency come up on Friday, and so I wasn't able to record live lectures for the rest of my sections. I also wasn't able to meet with a couple people who wanted to meet on Friday. So I pushed that due date to the end of the day today. And then we still have that kind of 5th Excel assignment, which is due at the end of the week on Friday at the end of the day, as well as that 5th Connect assignment. Here we go. Which is due at the end of the day on Friday as well, okay? All right, so I think that kind of gets everything out of the way. We can start going over this practice exam. So the formula sheet's gonna look a little bit shorter here. Really, you can think about what we've done since the last exam. The first kind of half was pretty computational. We were calculating confidence intervals for the difference between means and proportions. We were also doing some hypothesis testing, so we had our test statistic equations, but really those are the only equations that we needed, right? Other than that, we were kind of moving towards linear regression. And although you could kind of add in, right, an additional equation, which would look something like this, and I'll change the size here in a second. Oops. BN times xn, right? We could kind of think about, we had this linear regression equation that we were using. This doesn't really help you a whole lot, and hopefully as we've worked through a lot of the examples, you kind of know that every single time we see a linear regression, really what we're seeing is the results for this equation, right? Giving us our coefficient estimates. So probably do hardly any linear regression today. Towards the end of the week, I'll work through some more examples. But today, we're going to start with practice exam A. Right? Kind of starting off with this example, we're thinking about, maybe we think Indiana and Ohio has some differences in the health. I think it mentions in the problems what this is measuring. I probably could go back through and do a better job in this practice exam. I was trying to get some examples out quick. Here we've got measures of BMI for the two states. So we took 40 individuals from Indiana, found this average BMI of 27, a sample variance of 25. We took 50 individuals from Ohio, found a sample mean for BMI of 29, and their sample variance as well. So the way I've kind of displayed this, I've made it a little bit easier to identify, how we're going to look for the difference between Indiana and Ohio, right? I called Indiana group 1, Ohio group 2. So if you're looking at that formula sheet, I identified for you who group 1 is, who group 2 is for these formulas. So the first thing we're going to do is build a 99% confidence interval for what the true difference between Indiana and Ohio is, right? Group 1 was Indiana, group 2 is Ohio. Once again, I'm not going to make you compute the degrees of freedom for these two population examples, because if we only have sample variances, and we go ahead and we look at this formula sheet, I'm building a confidence interval for the difference in means, so I know it's going to be either this equation or this equation. I only have sample variances. So here, this is population variances. I only have sample variances, so I need to be using this confidence interval equation. The problem is, because I have sample variances, I have to use that student t distribution, right? The only time we get to use, the only time we use a standard normal is if we're looking at proportions or we know the population variances. So we're going to have to use that student t distribution, and the degrees of freedom is this thing delta, right? So if we want to really look at it, I've got another formula sheet, an older one. I might have taken it off here as well. Yeah, I did. So what delta is that crazy equation where I had, using the variances and the sample sizes, and it was pretty ugly looking. So I said, I'm always going to give you an assumed true degrees of freedom. So here, the assumed true degrees of freedom is 50. So I look at that confidence interval equation. I've got my degrees of freedom will be 50. I wanted the 99% confidence interval. So my alpha, remember that's the area outside of my confidence interval in decimal form. So 1% would be outside the interval. In decimal form, alpha is 0.01. But I'm dividing it by 2, so 0.005. So I've got a degrees of freedom of 50. And on each side of my confidence interval, I have 0.005. So what I can do is open up my student t table, rotate this around, blow it up a little bit. So what I've got, I want the area of 0.005 in each of my tails, but I want a degrees of freedom of 50. So degrees of freedom of 50, 0.005. Remember that was kind of my column heading, whoops. So go down here, 2.678 is going to be that t value that I want. So really it's just a matter of plugging in that t value of 2.678. And then from there, it's just plugging in what the problem gave me. Right? So the problem gave me the two sample means. So I would look at 27 minus 29, then add and subtract to that. 2.678 was my t value. Add to get the upper bound, and then when I subtract this, I get the lower bound. Plug in my two sample sizes. I think they're 40 and 50. Plug in my sample variances. I think they were 25 and 36. And then it's just a matter of being able to enter this into my calculator. Okay. Now, one thing I could recall is that when I'm looking at a confidence interval, what I'm doing is I'm looking at the difference that I found between my sample statistics. So those were what? 27 minus 29. And then I was adding and subtracting, that t value of 2.678 times all the other stuff I had here. So what I'm really doing is I'm basing this confidence interval around that sample difference I found of negative 2, so that -2 should be smack dab in the middle of my confidence interval, right? Here's my upper bound, here's my lower bound once I compute it. So if I look at all of those possible answers, they can only be the correct answer if -2 is smack dab in the middle. So when I go look at those possible answers, is -2 smack dab in the middle of A? Actually, look at that. Yes, it is. What about B? Yes. C? Well, actually, -2 is a lot closer to -1.2 than it is to -4.2. So I could rule C out, right? The difference between -2 and this lower bound is 2.2. And the difference between -2 and the upper bound would be, what, less than even 1, about what, 0.8? And then -2 isn't even in my confidence interval D. So I can rule out C and D right away. I could almost just like cross those out. So get my word guy here. So, right, those can't be the right answer. And then it's just a matter of making sure I can do the computation. Okay. So I think if I go ahead and do this, I've got what? -2 plus 2.678. And I'll work along, do these by on my calculator with you. So it's 36 over 50. So it looks like negative. So yeah, so the upper bound would be about 1.106 and the lower bound is -5.106. So there, once we do the computation, and there is an answer sheet on Canvas as well, but as I work through these, I'll kind of identify the correct answer. Okay. And if you have any questions, feel free to speak up or kind of type in the chat. I'll keep an eye on the chat once I get kind of through each question. So any questions on that one? Okay, so the next question is, what if we have this example where we want to determine the test statistic for a certain type of tail test? So let me make sure. I think I misplaced my eraser. I just want to make sure I can erase these in between. Where did it go? Oh, here it is. So we've got this test. Now, it doesn't matter what type of tail test we have, we would still compute the test statistic the same way. So I'll kind of pause on that. Really, I can't give a lot of guidance on a question like 2. The test statistic equations, to me, should be some of the easier ones on the exam. So once I identify what type of problem I have, so I'm looking at the difference in means, and I only have sample variances. So if I go to that formula sheet, here's my 3 test statistic equations. Well, here's proportions. Hopefully, I'm not using this one. I have sample means. So I'm between these two, and I only have sample variances. So here's my test statistic equation. We always use the assumed true difference of 0, so that numerator becomes a little bit easier, which is just, what's the sample difference I found? If we wanted to be real technical, outside of this class, we could see assumed true differences, that were something other than 0, but I said for all the examples I'll give you on the exam, that assumed true difference will always be 0, so we can almost just ignore it, right? Subtracting 0 doesn't change anything. So I'll plug in my 2 sample means, my 2 sample variances, my 2 sample sizes. This is really just being able to kind of get this entered in my calculator correctly once I've identified the correct test statistic equation. Now, similar, once again, remember, all these denominators of my test statistics all represent standard deviations. Okay? So the denominators will always be positive. So here, the sign of my test statistic is really just the sign of whatever the difference that I found was. So the difference in my sample means, remember we had 27 minus 29, so -2. So I know that my test statistic has to be negative. So right away I could rule out this guy here. And that's because the denominator is always positive. So from here, it's just a matter of computation. So it's just a matter of getting this entered into our calculator correctly. So let's see if we enter this in. It should get -1.725 if we kind of round it. Okay, so once again, I can't assist as much in the computation. One thing I can say, if you're having some issues replicating the correct answer, maybe computing this denominator first and then plugging it in, doing it kind of in parts, that might be helpful. But really it's about identifying the correct formula there. Okay? And we knew that was the correct formula because we only had these sample variances. Right? So instead, let's assume that now that we could calculate a test statistic, I think here I give you an assumed true test statistic. So assume that we found negative 1.55 and assume that the degrees of freedom is 50. Right? What would the critical value be at the 95% confidence level? So what type of tailed test do we have here? We go back to 2. We were given this assumed true test, or we were given the null and alternative hypothesis. So we've got a less than sign in the alternative hypothesis. So we have a left-tailed test. Right? So if we've got a left-tailed test, the critical value is going to be the value such that, so we look at this, it's going to be the critical value that will give us alpha in our tail. Right? Well, alpha here at the 95% confidence level, will be 0.05. Right? So the area to the left we want is 0.05, and we want the t-value, this critical value that should be the cutoff for anything greater in absolute value or anything more extreme than that critical value, we will be rejecting the null because we've assumed, right, that kind of that null hypothesis was that it was less than 0, so we assume it's 0. So anything I find that's past this critical value, this t-value that kind of gives me alpha in the tail, I'll reject any test statistic. I can reject the null if I see a test statistic in this range. Okay? So if I want 0.05 in the tail, I've got a degrees of freedom of 50. Well, before we go to the table, we know automatically that this critical value will be negative because, right, the student t distribution is centered at 0. The area to the left of 0 and to the right of 0, that's the mean. The area to the left and right is 0.5. So if I want the area to be 0.05, I know that I'm going to have a value that's to the left of 0 or a negative value. So we'll go to the table. Go to that student t table. We got a degrees of freedom of 50, and we wanted the area of 0.05 in that tail. So scroll down here. Okay, 1.676. That's my critical value. Well, not quite, right? The student t table always shows me the area in that upper right tail. So because it's a symmetric distribution, I know that if, what was it? Now I already forgot the value. I know that if 1.676 gives me 0.05 in the upper right tail, negative 1.676 will give me 0.05 in the lower left tail, which is what I wanted. So negative 1.676, that's going to be my critical value. Now here, once I have that, it's easy to make the rejection decision because there's no other options where I have the correct critical value. But just in case there were, so example for if I had said something like this, right? If I found a test statistic of negative 1.55 and I've got my critical value of negative 1.676, should I reject or fail to reject the null? Well, we look here, right? We just found our critical value, which was, hold on, I need a third hand, I need more hands here. So I've got negative 1.676. That was my critical value. Right. Where would negative 1.55 fall? Somewhere like right here. So my test statistic is not in that rejection region, so I would fail to reject, right? If my test statistic had been, say, like -2, right, then I would have rejected. But it was negative 1.55, not quite in that rejection region. So negative 1.676 was my critical value, and because it wasn't in that rejection region, I did not reject or I failed to reject. Okay. Any questions over any of that? Okay. Now, if I had asked on this example, what's the p-value, right? It'd be a little bit tricky, right? Because if I try to find this test statistic of negative 1.55 at degrees of freedom of 50, it's not there, right? I know it's in between 1.299 and 1.676, or if I made all these, think about these negatives since it's a symmetric distribution. So 1.55 would be somewhere in between these two. So I can't give you the exact p-value, but what I can tell you is the p-value is going to be somewhere between 0.1 and 0.05. Right? So if I had to kind of sign this, right, I couldn't give you the exact p-value, what I could do is say something like this, right? So let's see if I can write from this angle a little bit better. Right? So I know that my p-value will be somewhere between 0.05 and 0.01. And that's really all I can say. Okay. All right. So that would be, kind of works through that example. So the next one, we're looking at kind of proportions. Right? So we've got a recent survey, 500 men, 500 women, shows that 37% of those 500 men own guns and 31% of the women own guns. So 0.31 and 0.37 are my sample proportions. And 500 and 500 would be my two sample sizes for two groups. This one's kind of easy because I have the same sample size from each group. So if I wanted a 90% confidence interval for the difference between gun ownership of men and women, so once again, I've identified men as group 1, women as group 2, so men minus women, what would that confidence interval be? Well, if I go to my formula sheet, I want a confidence interval, so one of these three equations. I'm looking at the difference between two proportions, so it's going to be this guy right here. I mean, once we've identified the correct equation, right? And I mean, I guess I made it a little bit easy on this practice exam because I kind of, used the notation of sample proportion. But even if I had just told you that 30% of men own guns and 31% of women own guns, you've got proportions there. You're thinking about, how, out of 500 men, what proportion own guns, right? What percent, right? We can convert percentages to proportions pretty easily simply by dividing by 100. So if I look at that confidence, oops, that's not what I want. If I look at that confidence interval equation, I can plug in 0.37, 0.31, 0.37, 0.37, 0.31, 0.31, 500, 500. That's just information I was given in the problem. The only thing left I have to do is look up the z-value, okay? So I want the z-value that gives me alpha over 2 on each side of my confidence interval. So we wanted a 90% confidence interval here. So I can think about my alpha as the total area outside of my confidence interval in decimal form. So 10% is outside, or 0.1 decimal form. So 0.1 was my alpha. I have to divide that by 2 because I have an area on the left and right of my confidence interval. So 0.05. And I'm looking at proportions. Now, the formula sheet kind of reminds me that when I'm looking at proportions, I need to be using z-values or that standard normal distribution. So open up my z-table. And before you take the exam, I would suggest having these two tables, these files opened up. They can be found on the main page of the Files tab under or on Canvas. And I'll copy them and put them in the final exam practice material folder as well. So they'll be in two places there. So I wanted what? 0.05 in that lower left tail and 0.05 in the upper right tail. So 0.05 is the area. The areas are displayed in the middle here. So I'm going to hunt for what's closest to 0.05. Looks like it's these two. So negative 1.64 and negative 1.65. So I'll take the higher of those two, or the higher in absolute value, so negative 1.65. Now, another way of doing this, if I use my student T table, and I want 0.05 in my tail, if I go down to the very last row, where I have an infinite degrees of freedom, we said these values represent what I would find from a standard normal distribution. So I can get a little bit more exact here. It's going to be 1.645. Okay. So once I have that, plug that z-value in, I've got everything in there. So I'll add to get my upper bound, subtract to get the lower bound. And then there's just a matter of kind of computation once again. So let me do this real quick for you. So square root of 0.37 times 0.37 divided by 100 plus. So 0.109. So if we go to the answers here, the upper bound is going to be 0.109. The lower bound is going to be 0.011. Okay. Now, if I just think about what I was looking at, once again, I'm building a confidence interval for what the true difference in the population proportions would be. So if I think about that very first part of my confidence interval equation, I was taking 0.37 minus 0.31. So So I was building my confidence interval around a difference of 0.06. So 0.06 should be smack dab in the middle of my confidence interval. So if I look at those options, let's see if we can rule any of them out. I'm not sure we can here. So 0.06. Yeah, I think on this one, 0.06 looks like it's smack dab in the middle of each one of these. So I couldn't have ruled any of these possible answers out. Now, if I had instead, let's say I gave you something like this, right, where I gave you some negative values here. Well, 0.06 is not within this range, so I could have ruled that answer out. Okay. Any questions on that one before we keep going here? So now we've got, what would the test statistic be for this null hypothesis and alternative hypothesis? So on the exam, I kind of use both these because outside this class you could see something like this, but on the exam I'll always kind of give you this alternative hypothesis as H subscript A. Okay. Now, it doesn't matter what type of test we have, we always calculate the test statistic the same way. So if I look at my formula sheet, here's my 3 test statistic equations. So this is where we had kind of a little bit of a unique one where when I'm calculating my test statistic for the difference in sample proportions, right? I'm going to first have to find this p-bar. So I have the equation for p-bar right here. I plug in my sample sizes of 500, my sample proportion of 0.37, 0.31. Once I obtain that intermediate value of p-bar, then I can plug that in into my denominator. I then plug in the rest of my values, and I can compute this. Test statistic, right? So I'll do that here real quick. So 0.34 should be what you get for p-bar there, and we'll multiply by that. Take the square root of that answer. Should get about 2.002. So, oh, I think this one got cut off a little bit. So 2.002, if you were going through this, for some reason, I'll delete that. You didn't see that was one of the possible answers there. It was answered B. Now, right away, once again, if we look at that test statistic equation, our denominator represents a standard deviation. So if it's a standard deviation in the denominator, right, we know that a standard deviation will be positive. The difference we find tells us the sign of the test statistic. So once again, if we think about, here we've got 0.37 minus 0.31, and then something down here that represents the standard deviation of the difference between the sample proportions. Well, 0.37 minus 0.31 is a positive value divided by some positive value. Oops, sorry, is 0.06 is a positive value divided by some standard deviation, which we know is a positive value. My test statistic would have to be positive. So if we go back, right, and we think about, could we rule any of these possible answers out? Sure enough, we could have ruled out A here since it was negative. Okay. Okay, so the next one is what's the p-value, assuming that you found a test statistic of 1.45. So we found the correct test statistic, but to make sure we don't have cascading errors, let's assume it was 1.45. Assume that kind of the alpha that I'm using for my significance test is 0.05. I have an extra period in there, so I'll get rid of that real quick. So we can think about this as a 95% confidence level or the 5% significance level with alpha being 0.05. So I've got what type of tailed test here? Well, I've got a not equal to sign in my alternative hypothesis, so a two-tailed test. So I'm thinking about my test statistic, right? And I've got 1.45 as my test statistic. Because if I've got a two-tailed test, right, what I've got here is I'm looking at the standard normal distribution. I found a test statistic of 1.45. So the p-value is the probability I saw the test statistic that I did or anything more extreme or greater in absolute value. So I'll find this area. But for a two-tailed test, it would have been equally as likely for me to see something that was 1.45 standard deviations below the mean, and that would have equally went against the null. Because here, when I have a two-tailed test, it doesn't matter if I find it, if I find the sample difference above or below the mean, both of those go against that assumed true value, which is think about that difference is equal to 0. Okay? So I'll find this area, and because it's a symmetric distribution, I have two areas that are the same size. I multiply by 2, right? And that gives me my p-value there. Okay? So how do we do that? Well, we can go to our standard normal table. The standard normal table will tell me the area to the left of 1.45. I wanted the area to the right, so I say, okay, I had a test statistic of 1.45. So let's see if I can get this on. Here we go. 1.45. So 0.9265. Oops. So 0.9265 is going to be, all right, the area to the left. I wanted the area to the right. So I'll subtract that from 1. So I'm going to get what? 0.0735 here. I'll multiply that by 2. All right, and I should get what? 0.1470 if I multiply that by 2. So here looks like we've got 0.1470, right? 0.147. Okay. So that should be our answer. Now, if I was making my rejection decision here, would I reject or would I fail to reject? Well, we only reject if that p-value is less than alpha. So my p-value is 0.1470. My alpha is 0.05. This is, in fact, right, not less than 0.05. So I'm going to kind of do this here. So go to symbol. Oh, actually, I don't even know if they have a strike. There's probably one somewhere. I'm not going to hunt for it. So this is, in fact, not true, right? This is not less than, it's greater than. So that doesn't meet the criteria. So I failed to reject the null hypothesis here, because the only time I should be rejecting is if that p-value was less than alpha. Now, if I forgot to multiply it by 2, I would have had the wrong answer. Another thing that can, on these, that can sometimes be an easy mistake to make. So let's say the answer here was, let me think, 1 point. I think this is right. I'm trying to do mental math in my head here. I got a calculator. I don't know why I'm not using that. Probably because I'm stubborn and want to. Yeah, so that's right. So let's say this is a possible answer. If I had forgot to subtract that 0.9265 from 1, remember that 0.296 was the area to the left. I wanted the area to the right. If I had multiplied that by 2 and I had forgot to subtract it from 1, I would have gotten 1.85. But I should remember, this is a p-value. This is representing a probability. There's no way I can get a probability that's greater than 1. So if I forgot to do that step, I multiply by 2 and I get 1 point something, I should say, whoa, I forgot to do something. Okay, if I multiply by 2 for a two-tailed test and I get something other that's greater than 1, I probably am looking at the wrong area, right? I was looking at the area to the left, and I actually should have been looking at the area to the right. Okay? So that's how you get our p-value and make our rejection decision. It's not a question on here, but what if I instead had asked you for the critical values? Okay? So for a two-tailed test, the critical values are going to be the values that give us alpha total in the tails, right? So if I've got an alpha of 0.05, for a two-tailed test, what we should have been doing was, we're looking at that standard normal distribution because we have proportions. For a two-tailed test, I'm actually going to have a pair of critical values such that alpha total is in my tails, or alpha over 2 is in each tail, right? So if my alpha was 0.05, I should have 0.025 kind of in each tail there. So now I want to find that z value, right, or the two z values. It would give me 0.025 in the upper right tail, and 0.025 in the lower left tail. So I'll go to my standard normal table, right? I'll say, okay, I want the area of 0.025, so I'm going to hunt for that. 0.025 in that lower left tail, so negative 1.96. But I'll have a pair of critical values, so it would be positive and negative 1.96. I could have also used my t-table, right, and used this very last row. I wanted 0.025 in the tail, so 0.025 at the degrees of freedom of infinity, which represents the standard normal distribution, 1.96. But recall, we've got two critical values, so negative 1.96 and 1.96. Okay? This does not look like one here. 1.96. Okay? So that's how I would have found my critical values. And then there, if I wanted to make my rejection decision, I believe we found, what did I tell you? This test statistic was 1.45. So I would plot that test statistic of 1.45. Clearly not in my rejection regions, right? Not more extreme than either of my critical values, or not larger in absolute value than my critical values. So once again, I'd be making the same rejection decision, which is that I fail to reject. Okay? So for a two-tailed test, when I look up my critical values, right, I have to divide alpha by 2 because alpha is the total area in the tails. For a one-tailed test, alpha was all in one tail. For the p-value, once I found the area that was kind of more extreme, so for the positive test statistic, it would be something that, the area to the right. For a negative test statistic, the area to the left. Once I found that area, I had to multiply it by 2 for a two-tailed test to get my p-value. For a one-tailed test, I didn't have to do that, right? All right. So, did we answer? Yeah, I kind of circled that. And I added an additional kind of question there that you could see on the final exam. Okay. Got enough time? Yeah, I'll work through these. So let's try these 7 and 8 here before we end today. Any questions? Okay. So any questions on any of that before we kind of do this last example? All right. So let's say I've got this example where someone's looking at, whether people consume fewer calories at McDonald's after they post the calories to the menu. We get 42 individuals in our sample, and we look at the difference between what they consumed before and what they consumed after. So we're calculating kind of this new variable, which is the difference between before and after for each individual. Once we've done this for all 42 individuals, we find that the average difference in their calorie consumption was negative 50, and we found this sample variance of 22,500. We want to see whether or not posting the calorie information decreased calorie consumption. So even in these sample kind of practice problems, even though I'm giving you the null and alternative hypothesis, make sure you understand why that is what it is. Because a potential question I could ask on the exam is, suppose they want to test for whether or not calorie consumption has decreased after they posted the calories. Well, if we're thinking about whether or not it's decreased, and the difference you're looking at is after minus before, the only way that this difference, if it's decreased, after would be smaller than before. So you're really thinking about, is that difference negative or is it less than 0? That's what you're trying to find. So if you want to find is that difference less than 0, you assume the opposite is true, which is that that difference is greater than or equal to 0. So here we've got a left tail test. How do we find our test statistic? This one, actually, I'm going to have to add that. I'll add that into the formula sheet. I don't know why I forgot to add those in. So, where is that? Okay, I'll add those in. I thought they were on here, but I guess not. I'll update that final example formula sheet. So when we're doing these sample difference ones, the formula that we're going to end up using, and I'll next class make sure I point out, or the next recording, I'll make sure I point out where that is on the new formula sheet. But all it's going to be is take that sample difference minus the assumed true difference, which we're always going to use 0, and then divide by the variance of that difference variable divided by our sample size. So here we had what? 42, 22,500, and this was 50. Right? So once we plug all those values in, these matched pairs examples actually should be relatively easy. Okay, so if I compute that here real quick, so we got what? 50 divided by the square root of 22,500 divided by, I think it was 42, so 2.16. I can't remember if it was 50 or no, it was negative 50, so it'll actually be negative 2.16, right? Because that sample difference that we found here was negative 50. Okay? So once we have that test statistic, right, that's good. We could do the critical value approach. and see, does that test statistic fall in the rejection region? So for this test, if I wanted to find a critical value and determine the rejection decision, assume that I, instead of finding negative 2.16, found negative 2.5. What would the critical value be, right, at an alpha of 0.05 for a left-tailed test? Okay. So I've got a left-tailed test, right? I want the critical value that gives me 0.05 in that lower left tail. But remember, I only had kind of this sample variance, right? So I should be using that student t distribution. Okay. So what's my critical value here? It gives me 0.05 in that lower left tail from a student t distribution. Well, if we look at this student t distribution, for these matched pairs examples, the degrees of freedom went back to being easy. It was simply n-1, very similar to when we had a one population example. So 42 minus 1 would be 41 degrees of freedom. I wanted 0.05 in that lower left tail. So 1.683 is my critical value. But remember, we did a left tail test. So my critical value, remember the student t distribution is centered at 0. So that critical value should be negative. So I'll take that 1 point, I already forgot what it was, 6 something. Here, let's go back. 1.683. But because it's a left-tailed test, negative 1.683 will be my critical value. From there, if I have a test statistic of negative 2.5, where would that fall? Somewhere over here, which is clearly in the rejection region, right? I think about, I've been shading this in, but I could just be drawing arrows, for a left-tailed test, draw an arrow in the left tail. For a right-tailed test, draw it to the right. For a two-tailed test, I would draw an arrow kind of in either side of those critical values. And if my critical value falls, if my test statistic falls in that region, then I can reject. So here, I clearly have an example where I can reject the null. So negative 1.683 should be our critical value. So let's look at the answers here. Negative 1.683. Didn't want to do that. And I reject the null. Right? Should be our answer. Okay. Now, because I knew it was a left-tailed test, hopefully, I look at this and I think right away I can rule out answer D, right? Because it's a positive critical value. For left-tailed tests, we should only have negative critical values. If it was a right-tailed test, then I would only have positive critical values. If it was a two-tailed test like we had up here, even though it wasn't one of the questions, we said, well, I would actually have pairs of critical values, plus and minus whatever the value was. Here, I think it was plus and minus 1.96. Right? Any questions on any of that? So that got us through most of this first exam. The only thing left is some linear regression stuff. I'm actually going to add in some more, kind of like another practice exam. It'll be specifically just some linear regression problems that don't show up on these kind of first two. We'll probably work through the end of practice exam A and start on practice exam B on Wednesday, kind of just reviewing that, unless you guys have any specific problems or specific questions. Other than that, feel free to reach out if you want to kind of make some small changes or kind of add to that fourth Connect and Excel assignment today. You can do that by the end of the day today. And then as you're working on that fifth Connect and fifth Excel assignment, feel free to reach out. I'll be available all week via email. We can kind of set up some Zoom calls. I've done a few of those. Other than that, there's no questions. I'll wait for a second here if you guys have any questions. Otherwise, I will see you on Wednesday.